Hello and welcome everyone. My name is Hannah Mason. I'm an associate editor at CompositeWorld. I want to thank you for joining us today for this webinar titled Improve Productivity and Reduce Flow Time in Fiber Placement Through Real-Time In-Process Inspection, brought to you by CompositeWorld and presented by Fives Composites. So we have two presenters today. Our first presenter is Robert Harper, Technical Sales and Market Development Director at Fives. Robert has worked for Fives for the past 29 years. He has held various positions, including leading manufacturing teams responsible for the assembly of composites processing equipment. In his current role, he works directly with large aerospace companies and component suppliers. Our second presenter is Gil Lund, Program Manager. He has 26 years of experience in instrumentation, sensor research and development, data analysis, and industrial Internet of Things and edge compute platform development. He has been with Fives for 15 years, and in his current position, he focuses on strategic technology capabilities, specializing in custom industrial robotic solutions, as you see on the screen here. So before we get started, I just want to let everybody know this presentation will last about 40 minutes or so, followed by a question and answer. So if you have a question, feel free to type it in at any time during the webinar in the question field in your GoToWebinar control panel on the right of your screen. This webinar is also being recorded, and when complete, will be made available to you via email from CompositesWorld. That's all I've got. So Robert and Gil, it's all yours.
Thank you, Hannah. Thanks for the introduction. Thanks everyone for joining us today. I'll go through quickly.
Thank you.
Go through quickly the agenda. We'll do a quick introduction of just Fives and how the companies are grouped. I promise to be the only sales pitch. I will talk about the challenges and opportunities about the inspection, and then Gil Lund, my colleague out in Seattle, will take care of talking about the next generation inspection solution, return on investment, and then I'll come back with I'll take care of the summary, and then we'll have open questions and answers. We'll get started from here. So first, the introduction, real simple, high level. So Fives, we're a large industrial group, $2 billion company, divided into three main sectors. And I'm only going to talk about the one that this composite group is part of, which is the high precision machines. As you can see here, within high precision machines, there's still 7 groups or smaller companies within that. And the companies that we're talking about here is the Composite Automated Solutions. And it's made up of 3 companies. Fives Cincinnati, you may know as MAG or MAG Cincinnati or Cincinnati Millicron. There's Force Linné out of Captainac, France, and then there's Fives Lund out of Seattle. Lots of years of experience amongst all 3, but like rich history and industrialization combined or married with innovative spirit. So let's get into the presentation. Really, it's the challenges and opportunities for composite manufacturing when it comes to inspection. So high level overall manufacturing process for composite parts is you have a layup, and different from metal cutting, you have to inspect every ply. So you put a layer down, in a lot of cases the thickness of the piece of paper that you're writing on now, and then you have to go back and lay the next layer and then inspect, repeat and repeat and repeat, and then move on to cure, and then also ultimately, once the part's cured, to non-destructive testing and then to assembly. So we're only going to focus on today the ply by ply inspection portion. So first of all, what are we looking for? So there's 9, I'll call 9 groups. First, gaps, individual and cumulative gaps. So I'm looking for gaps in between toes. I'm also looking for overlaps. Not only if there's a gap, most likely adjacent to that will be an overlap. And then I'm looking for missing toes. So in this area here is a toe that it's actually missing. And again, I'm going to assume that you know what a toe is and you know what fiber placement is. The next 3, I'm looking for ply boundary. So I have to make sure that the ply itself is positioned in the correct place on the part. I'm looking for also the orientation, to make sure that the orientation, if I say lay it in 45 degree, that it's ultimately laid in a 45 degree, and I'm looking for toe splices. So here is where toes are spliced together by the material manufacturer. I have to be able to identify those not only on that layer, but also keep track of where they are on underlying layers. And then the last group includes topical features, which are twist, and in this area here, wrinkles, and also we can call puckers, no technical term. Bridging, so when you go up over top of a feature, to make sure that you have good adhesion, to make sure there's no bridging, and then also FOD, which is foreign object detection. So where someone may have dropped something on the part, backing film or somewhat similar. All 9 of these features or groups need to be identified. So how do we identify them? So that today there's 3 primary methods of identifying or inspecting. The first one is human visual inspection, we'll call HVI. There's inline inspection, I'll call that ILI, and then there's in-process inspection, which is IPI. So first is the human visual inspection, self-explanatory. You lay apply. A human goes out with some sort of handheld device or with the aid of an overhead laser projector or template, and verifies that not only that the boundaries are correct, but also scans the entire part for gaps, for laps, all of those 9 categories that I showed you before. As you can imagine, this is extremely labor intensive. The larger the part, the more labor intensive. Very easy to miss things. So this method, unfortunately, which is probably the most widely used today, greatly decreases overall productivity. And one of the key things, and you're going to hear this repeated several times throughout the presentation, is the non-compliance is determined after the layup is complete. After a ply or a course is complete, that's when the non-compliance is identified. So the next is inline inspection. So inline inspection is a device, in most cases, some sort of a laser scanner device that's either mounted on the machine, collects data as it's laying, or a device that scans the ply after the ply has been laid. And for the inline inspection, also the data is collected but not compiled until the conclusion of that particular course or that particular ply. So all non-compliances again are identified after they've been laid. So some sort of an overhead laser template points out where the non-compliances are, and someone goes in and does the rework. This itself is a big step forward in over HVI, so the human visual inspection, but still there's a lot of we'll say time used, and mainly in the rework portion, because when non-compliance happens, it still needs to be reworked because you've allowed the machine to lay the non-compliance. The third, which is what we're here to talk about, is in-process inspection. So in-process inspection is a system that's mounted to the machine. It's integrated into the machine. It's able to detect as defects or non-compliances happen. It's able to stop the machine, to inform the operator, send a message to the control, and give them options to stop the process. So imagine a part, 22-foot diameter, 40-foot long fuselage for a commercial aircraft, a 45-degree ply where you helical wind the material, and at the very beginning of the course, the toes are all short, or 1 or 2 of the toes are short, it doesn't matter. And you allow the machine, in both HVI and in inline inspection, you allow the machine to lay the entire course, and then only to tear up or peel up, there's no magic way, to peel up the course that was laid and relay. What this system allows is it stops the machine, it informs the operator within 1.5 seconds, so about 4 inches of layup, that the toes are short. It knows that they're non-compliant, and it allows you to abort the course and restart the course. So the big difference here is it decreases drastically the rework. So let's look at 3 simple examples of the 3 methods. So this is just an example, or a example part. I'm going to call it a mid-sized composite part. It has 75 plies or ply groupings. The part program cycle time is going to stay constant between these 3, which is 8 hours. Process related out of cycle activity. So loading material, loading the tool, unloading the tool, maybe some cleaning of the machine during the process. And then the last category is inspection and rework. And in this particular case, human visual inspection, I'm going to say there's 5 minutes per ply, and that allows you to inspect the part and then also to do any type of rework that's non-compliant of those 9 categories that I showed you earlier. So you have a total of 18.25 hours to lay this particular part. The same part, but using inline inspection. And really the big change, the only change, is the inspection rework goes from 3 minutes, or from 5 minutes to 3 minutes. The HVI, or the inline inspection, or the ILI, is a huge step forward. As you can see, it's a 14% decrease in inspection time, because you've really eliminated that human piece of inspecting, but you haven't fixed the rework portion. You still allow the machine to lay the bad non-compliant course and reply. So that still has to be reworked. So in this case, I've reduced the overall time per ply by 40%, which gives you an overall net floor-to-floor improvement over HVI of 14%. Again, a step forward. What we want to talk about today is the next step, and then that is the inspection rework dropping to 1 minute per ply. A big difference here is inspection time still happens. Some rework or inspection time is automatic, similar to the inline inspection system, but the rework is drastically reduced because you stop the machine immediately when a non-compliance is identified. Dropping that to 1 minute per ply, and then you can see over HVI is a 28% improvement in overall floor-to-floor. So before I pass it on to my colleague, I want to first talk about the development team. This was a collaboration, this technology that we're going to talk about here today, between the National Research Council of Canada, which the Aerospace Research Center out of Maribel, Canada, led by Ali Yosfer and his team of PhDs and researchers, where they brought sensor technology and some algorithm development to the party. Our facility in Seattle, Washington, Lund, which they had lots of experience in other types of inspection systems, and then also data collection, high performance data collection. And then also the Cincinnati facility, the offline programming system, the AIP technology, and in application engineering. Those are the key contributions to the development team. From here, I'm going to pass it on to my colleague Gil Lund, and Gil's going to talk about the nuts and bolts of the system and how this system differs from others in the industry today and the value that it brings. Gil?
Thanks, Robert. And thank you to CompositeWorld. Webinars have been a great way to keep in touch in 2020. So excited to be sharing this innovative technology with you. There's quite a bit of content for me to cover. I'm going to be a bit accelerated, so hold on, keep with me. So first, let's briefly go back in time when we branched out on this path. At this point, we had already developed an in-process inspection solution for automated tape laying. It was on mildly contoured parts, wing skins to be exact, and we were tasked to implement inspection on automated fiber placement. So this is our development charter, where you see here, these requirements came after lots of internal feedback, voice of the customer, were prioritized and given to us, and we stack rank them. So as Robert told you, the first and primary requirement, which is pretty obvious, it's to minimize the overhead of inspection. We have to realize the pie chart. That's compulsory. And then the second requirement, which pairs with that, is we have to be able to measure all the critical features that AFP needs to inspect. It doesn't do any good to only inspect part of the feature set. So once you have that, you have to add exceptional performance on contoured parts, right? This is a requirement that forced us out of our box. We really didn't have a solution back then on how to get this figured out. We needed to consider an alternate sensing paradigm. improved resolution. Now our stakeholders were really raising the bar, right? We definitely had to find another sensing solution because high performance and high resolution don't always work together. Sometimes they work against each other. So along with the part contour, we no composite surfaces are not smooth, right? And successful solution would have to pick up on the subcontour, the substructure, and the pre-preg surface that you see in these photos. You see the embossment of the laminate surface underneath. And these images are actually from our sensing solution. So that's exciting that it can pick this up, and that's what I'm going to describe. Lastly, minimal material sensitivity. Anyone who has photographed or scanned an uncured composite surface knows it's really hard to get a good picture. It's low contrast. There's a lot of variable sheen. It's hard to dial in. The fiber matrix formulations are all different, and it's a very custom solution. So combined with the need for sufficient image, we had a challenge ahead of us. So this charter is why we partnered with Ali Yosefer's team at the National Research Council of Canada, which I'll just correct a little bit. They're out of Montreal, not necessarily Mirabel. Mirabel is a suburb of Montreal, but they're primarily from Montreal. And they had a game-changing technology which checked all the boxes in our charter. So there was a strong partnership formed and to introduce this technology to the composite world. So the technology is called optical coherence tomography, OCT. It's laser-based volumetric imaging, right? The word tomography used, and it's analogous to ultrasound, right? So ultrasound is another volumetric imaging, but it uses optical waves, right? Laser light. It's mature. It's been used in the medical industry for many years. And in our context, we were enabling OCT for an AFP application, using it as, right now, we're using it as highly robust surface profilometry. You can see some of the images where it's used in the medical image field. All right, so here's the science behind OCT. I don't have a lot of time to go into all the details, but I'm going to point out the basics and describe the key benefits. The version we're using is called swept source OCT because it's an energy source is a laser capable of providing light over a range of wavelengths. The light is then split into two paths, which is you see here called the reference and sample arms, which is a standard interferometry. So interferometry is a technique that's been perfected a lot in the last 100 years and used to measure very precisely on things that are far away with no signal loss, very small signal loss. And I'm sure a lot of you have heard it. You know, when you talk about the search for dark matter and the discovery of gravity waves, they all use interferometry. So how are we enabling this foundational technology for composites? So the one reason we use this is this measurement technique enables the source and the measurement hardware, which are shown in the green and red outlines here, to be decoupled. And this provides many advantages. The main advantage is allowing for a scan head that is compact, rugged, and optimally mounted on an AFP head without constraining the machine movement. The scan head can also be synchronized with the position of the machine at the point of measurement. In other words, before the signal is measured. And I'm like, synchronizing photons, that's to me really amazing. That's real time. So this feature, when it was first introduced to me by Guy Lamouche, who is the father of OCT at the NRC, or the application of OCT on composites, I was blown away. So lastly, what excites me about this slide is what it doesn't show. There is no optical camera or traditional imager in this design. Yeah, and that means there's no gazillion megapixel piece of silicon that's using some space age quantum physics to convert photons to electrons, and finding out that most of that data is thrown into the garbage anyway, which has been a major bottleneck. So our OCT system only processes the actual data which you see with these wave packets below and digitizes them using this custom data acquisition card paired with massively parallel processing architecture. Super cool. Hats off to the team at the NRC for getting this developed. So now let's focus on how OCT technology can solve our development goals for composite inspection. As I described on the previous slide, we can engineer a very compact sensor head. This head employs a confocal imaging path, meaning the source light is emitted and received at the same point. In fact, it's the same optical fiber. This provides immunity to stray and ambient light and electrical noise. Remember, photons have no mass, therefore they're not influenced by stray electrical field. The confocal imaging path also allows us to position our measurement system very close to the point of compaction or material layup. Rule number 1 of inspection, inspect as close to the point of application as possible. High dynamic range. This feature is cool, but needs a little more explanation. Remember, there are no camera imagers whose pixels can be saturated or starved of photons here. Just a data acquisition card that is capable of detecting this massive range of incident photons. Therefore, the system can pick up a much lower or higher amount of returning energy, and this gives a big dynamic range for our measurements. The final key capability of OCT is it's not sensitive to the incident angle of the laser to the surface. Without the articulation of the robot on a contoured surface, the angle in which the sensor intersects the surface can vary a lot for AFP. Our system is designed to have a nominal angle of 20 degrees. We can sneak it right under the compaction roller. So as you can see, OCT fits perfectly into the role of a world-class inspection system. So now let's go back and before we continue about OCT, let's see how it compares to the incumbent technologies which have been used before, called line laser triangulation, or LLT. LLT technology has been used for over 30 years and it hasn't been really approved much in the last decade. They've gotten blue lasers, we've gotten faster processors, we got bigger imagers, which have been a problem, and no features that make it better for composite inspection. The upside is that these are mature offerings and we know if they work for a specific application, then we use them. Thieves even has developed a custom line laser triangulation solution for our ATL, which you see on the right. So yeah, so it's sufficient solution. You can see from the camera here, if you keep the sensor parallel, roughly parallel to the surface, it works. Soon as you get on a high angle, you'll see dropouts or blooms where the imager is being saturated or starved of light. Packaging is also an issue. Trying to get that geometry, that triangular geometry, to fit on the back of a machine head is difficult and makes it inappropriate for AFP application. So here's a table showing side-by-side comparison of the Thieves OCT, Thieves NRC OCT solution to line laser triangulation. The first two items are the sensing configuration and the incident angle sensitivity. As I outlined earlier, and the schematic on the left shows, OCT has a confocal sensing geometry configured to scan at 20 degrees. So this is perfect configuration for attaching a sensor to the back of a machine head. Line laser triangulation has a triangular sensing configuration, and therefore you have a fixed scan angle that has to be orthogonal to the surface. So anything beyond about 10 degrees and your signal gets severely degraded. The next item is dynamic range, which I also explained. With composite sensing, there is a large dynamic range. The OCT can pick up a lot of difference without losing signal, and LLT can't. Therefore, a benefit of this dynamic range is we get to see a lot of the different prepreg materials and we don't get fooled by all the varying surface reflectivity that different prepregs provide. And lastly, the profile fidelity, which is the ability of the sensor to produce an actual surface, is a much higher with the OCT sensor. The basic reason is that each profile point is measured hundreds of times to confirm its accuracy and minimize measurement noise. So for LLT, the software, you need software to clean it up after the fact, after the imager is already processed and either lost or you know, the data is frozen. So next. So along with a spec comparison, here's a visual comparison of the same course measured with both LLT on the left and an OCT sensor on the right. So the top two images are just regular camera shots, so you kind of see what the course looks like. There's 6 patches here. We zoomed in on patch 3, which has an interest, and we like to look at a location where a gap turns into an overlap, right? So as you see, there's a gap on the right that's converging to an overlap on the left. And the image on the left is OCT. Sorry, the image on the left is line laser triangulation. The image of the right is the same patch using OCT. And so these are not camera images. These are the heat map that are stacked on top of each other. So these are the sensor images. And so you notice that this OCT produces a much clearer image and shows more clearly the transition from gap to overlap. And you also notice the number of points that we're taking in this, in the last 3 images. We a lot more measurements inside of the feature, right? We always want to look at how many points inside of the feature because that's defining how you can process that algorithm. As with many devices, everything has limited deadband region, and that's where the feature goes to 0. So OCT, that happens somewhere between 5 and 10 thousandths. Okay, so hopefully you're still with me. We're on the next chapter, which we describe the electrons, the role of the electrons and the bytes in this whole story. So even a great sensor needs to be paired with hardware and software that massage the sensor into information. On the left, you'll see all the elements of the processing stack for the platform. I remember when the stack was only a few layers deep, right? And obviously it's a pretty rich stack now. There's a lot of layers, so we're gonna go through them all. There's 4 computer actors in this story. So they facilitate the inspection plot that we're gonna tell here. First, the existing AFP technology on the top. And then on the bottom is the inspection technology that pairs with it. So starting on the right, the offline programming computer, every composite manufacturing environment has a computer whose job is to convert a CAD model into plies, courses, and toes used to make a machine program. We call our offline programming system the Advanced Composite Environment Suite, or ACE for short. ACE has been enabled to produce the key inspection assets required for mapping the as-designed part to the as-measured surface. So expected gaps, laps, toe end locations, diverging, converging course info, regional disposition criteria, all the stuff an operator gets from a plybook. So we call it the digital plybook. Paired with ACE is the tried and true Phoebs Viper AFP contour control system. This is the computer that's been enabled to synchronize with the sensor data acquisition and provide the head location, or more precisely, the tooltip pose. So we can't do much without measurement that doesn't have an accurate location. So let's describe. So now the second 2 pieces below are the pieces that we're going to describe in more detail. They're a little more involved, so we'll keep going. So all measurement stories start with raw data. Here's the basic view of how photons get converted to electrons, which then get to bytes and image frames that we call surface profiles. You saw how OCT was measured data at a single point. And now you can see how that, here it shows how that point turns into a full profile. the schematic of the laser scanner is at the top, and all the grouping of the red dots show one scan. Each dot is actually represented by one measurement wave packet, which is decoded into a peak position using a fast Fourier transform. And then hundreds of these dots, or A scans as we call them, are taken in order to really accurately measure the location of one position. In other words, that point is really accurate and correct. And it's repeated many times across the profile. So here's that layer. If you run the animation, Robert, I think it's a good way. After you take an A scan, you repeat it across the profile, and we do that thousands of times. So now the job of the quality control computer is to take that profile that comes from the sensor and combine it. We have synchronized it, which seems like a compulsory thing, but it's very important that sensor data is synchronized very precisely with the motion of the machine. I like to use the analogy of a digital oscilloscope. It's a job that it takes multiple signals to synchronize them, and some people in the industry call it data fusion or sensor fusion. Next. Okay, so now we're getting to the good part, right? That was all just set up. Now we have good data, and we can start really comparing it accurately to the part. So this step is called simultaneous location and mapping, SLAM for short, and it takes raw sensor profile as an input and combines it with the plybook that we received from ACE, and also takes the sensor data and transforms it, right? Sensor data is defined in its own coordinate reference frame, which is confounded by the motion of the head during layup. So if you look at the shades of blue in the sensor measurement image above, this is not due to the part surface, but it's an artifact of the head rocking forward and back, as it goes down the slope of the part. So that needs to be corrected. We can do this because we have the map from ACE about how the machine tooltip pose, and we also have the location of the machine. So we can build a virtual surface and compare it to the as designed surface comes from the CAD to give us a true digital twin comparison, which you can see in the middle. And then as all the plies are built up, you really can see the final part, which then can be extended in a future application to looking at the as-built assembly. To me, this is really an enabling technology. Next slide. So here, next we have to use this for inspection, right? So the digital twin is really just a placeholder to be able to find the defects, and the processing step was, some of these defects we just detect, some of them we have to measure. So pictured here is a photo on the left. Sorry, it's a little small, which we had a bunch of defects introduced. And in the yellow images, you'll see the sensor's view of those defects. So there's splices, 2 splices, there's a twist, wrinkle, missing toe. And then on the next slide, we show the defects that we have to measure, right? So we can't just detect, we have to detect and provide the dimensions of each of these to have a specific criteria of pass or fail applied. So this is an overlay. It's a little hard to see with the zoom here, but it shows gaps, laps, and toe ends, start and end toes. Next slide. So the last processing step is to determine if the measured feature meets the threshold to indicate whether it's a defect, right? So gaps, laps have different regional criteria along with, so in gaps within a course, gaps between a course, gaps in every region, you need a kind of a lookup table to make sure you're applying the right specification. Next. So the cool technology that Robert described, he showed about being able to give real-time in-process ply boundary location. So most ply boundary implementations require an OLT, which has to align to a part and project the laser line like you see in the background, which is inferred by either a human or an optical camera. So neither of which are real time. So our system measured the ply boundary ends and provide real-time feedback to the control system if it sees that dreaded short add, right, which you kind of see in the background here. And we know that that material is going to have to be pulled up. Next. So we're getting to the end. The last piece is to report the results. And if there's no rework, we move on. If there's some rework, how do you describe to the operator how to do the rework efficiently, giving them a task list? And then there's a lot of opportunity around this data for statistical process control and corrective actions, right? So if you find defects that all have familiar patterns, we've worked a lot with being able to correct the program, correct the machine, correct the process. There's all the different aspects that need to go through the formal corrective action process. So that's back to that slide. So hopefully that makes a lot more sense now that I've given you this overview. I know it's a lot of information, and please reach out to us if you want more slow-paced and in-depth version. There's a little video that we shows that gives the basic process running through a course. So final piece is here, what's the return on investment calculation, right? We know that everybody needs a model for return on investment. And the best model that we found is how does it relate to operational efficiency, right? So OEE, operational effectivity and efficiency, is the benchmark for deciding how well your machine is running. And we know we just need to optimize your fully productive time, right? So the ratio of planned production to fully productive and all these losses that cause you to derate your operational performance need to be mitigated. So the three areas, how do we improve that with in-process inspection? So the one Robert expected or gave you, which should be fairly obvious, is ply by ply inspection using HVI or inline inspection. Is we replace the measurement with in-process inspection. So that one's fairly obvious. But what's less obvious is the performance and performance improvements. So many times the setup of an AFP process is not optimized, whether it's from a change in the physical relationship of the machine and the layup tool, or from machine program that wasn't properly validated during the new product introduction or engineering change notice. And it requires, a skilled person to get everything dialed. An IPI system surface scan can provide empirical data during the setup of the tool to compare the as measured part to the as designed part, and it hence provides closed loop new product introduction, which is a big benefit. So a part of that must run, a part that must run slowly in order not to produce defects can usually be resolved by tweaking the machine program to lay it in a more even fashion. And it almost looks like you've put pressure sensitive film on your entire tool when you look at the data. So the other issue we see a lot is the impact of the feed rate override jockey. So if you have an AFP machine, you know this story. It's the operator who has control over the layup speed dial to modulate the head during problem areas of the layup where the program has not been optimized. The problem is that he or she can either lay up too fast and create defects or too slow without defects. Both situations cause variable performance and missed delivery schedules. So a fully optimized NC program prevents this unexpected OE hit. Lastly, both first pass yields and rework are reduced with IPI. Again, Robert explained that pretty well. All right, so how do you take these opportunities and develop a return on investment model? I've been doing these calculations for over 20 years and they don't change much. And no manufacturing manager is going to approve adding something to their machine that does not directly improve the bottom line, right? So the ROI model must weigh the increased non-recurring cost of the extra automation versus the decrease in recurring costs over some time horizon, right? That's pretty obvious. So in the previous slide, I outlined some of the primary cost savings or productivity improvements. And I wanted to highlight also there are indirect or secondary cost savings which are harder to assign a monetary value, but are still very real. So for example, the increased control over the process and optimized machine program has been shown to reduce the variability in your part stack up. So how does this consistency in geometry improve downstream fit up, right? Could it eliminate a shimming or painful jig and match drill operation to mate two parts? So what's the cost of quality escapes and part recalls? Remember news about Kobe Steel a few years ago? We almost went out of business when it was uncovered that their quality inspectors falsified inspection report because they allowed them to do manual inspection. Regulatory requirements, training, all of these things become more standardized and less human intensive or human technique intensive. Lastly, the quality of work is improved. So we all know retaining good employees is a key strategy for our companies, and eliminating the demeaning work that goes along with this legendary TED Talk here by Barry Schwartz is how you retain a workforce, because you get rid of the work that humans weren't meant to do. Manual or inefficient inspection is some of that work. So if you haven't really thought about these issues, please contact us. We have a validated ROI model for automated inspection, and we really would love to share it with you.
Okay, thanks, Gil. Great job. So what I'll do is finish up with the summary of what we learned today, and before we get into questions and answers. So quickly, there's three methods of inspecting composite parts, which is the human visual inspection, the inline inspection, and then the in-process. The key difference between the in-process over the other two is that in-process identifies and does an action before or at the time of the non-compliance, as opposed to the other two, which wait until after the end before they compile and or to scan, and rework still happens. The next is IPI reduces inspection rework labor. That's the big, it saves time clearly on inspection, but the lost time to rework, because you allow the machine to delay on non-compliance, is greatly reduced. OCT offers huge advantages over the current LLT. Like Gil had mentioned, just a couple. One is the different sheen or dullness of material, different types of material. The other big one, which maybe we didn't point out as much, is that for fiber placement, one of the biggest faults of the LLT system, the line laser triangulation, is that when you get off angle by more than 10, 15 degree maximum, it's really not very effective. The OCT system, we've laid up to 45, 50 degrees off angle, and we still get
60 degrees.
60 degrees, thank you. And we're still getting 98% of the points. So still great feedback. The next is it's mature medical technology applied to composite inspection. So we didn't invent a sensor here. We were fortunate that the NRC and Ollie came to us with this OCT technology and saw that this had a place in composite inspection. So we're just applying that mature technology. I believe the first OCT sensor was implemented for eye disease back in 1991. Next is this system is able to identify all 9 defect categories that I talked about. There's sensors out there today that can do 7 of the 9, 8 of the 9, 6 of the 9. This one can do all 9, so that it does eliminate that need for human visual altogether. And then, like Gil just talked about, the ROI benefits. A big benefit is 2 of the main ones. One is the reduced rework, which is cost, labor, and it gives back added capacity to the piece of equipment. So just high level. Okay, so that's the end of the presentation. What I just want to point out before we do questions and answers here, there is a link. If you select the link, we can set up a one-on-one with myself, Gil, or whoever we need to talk about your particular either need or interest. If you need more detail on how the system works, or you want more detail on how it can save you money. If you click the link and sign up, we'll get back with you. We'll set something up that we can get together one-on-one and go through it. So, okay, for that, I'll open it up to questions.
Great. Thank you both for the presentation. It's very informative. Like I think Gil said at one point, a lot of information to cover on this one, but I think you guys did a great job of breaking it down and walking us through it, so I appreciate it. So we do have a few minutes now, like Robert said, for questions and answers for our presenters here. So attendees, remind you there's a question panel on the right of your screen and the GoToWebinar control panel. Feel free to type in a question over the next few minutes here, but we will start with a few that have come in already. So let's see. First question, can this system be integrated with machines that are not from Fuse and or not using the ACE system?
Okay, so I'll take that one. And the answer is yes, it depends. Not a clear answer, but this is integrated into the control and then also an offline programming system, which is utilizing the design data. So it is on a one or individual basis, so we'd have to determine if it's possible. But yes, we would be interested in integrating this on a non-feed piece of equipment if that was if there's a desire.
Okay, excellent. Next question, what is the maximum number of plies or total uncured composite thickness that OCT can scan?
So it does it on a ply-by-ply basis. So the amount of plies doesn't matter. The overall thickness doesn't matter because I measure as I lay. So each layer of 7.5 thousandths thick, we are collecting data. That data then is stored, and we can tell through the layers where all of the, let's say, overlaps, the gaps, anything, all of the data is collected and we know in a particular region. So it scans as we lay each individual layer. So the overall thickness of the part doesn't matter to us.
Okay, great. Does carbon fiber dust affect the laser?
That's a good question. As far, yeah, carbon fiber, the lens itself, because of where it's located on the machine itself, we've not had any issues with that, with dust. So we are in a production environment with this on a machine today, and I would say today, I don't know for sure, 100% sure, but as of today, we've not had issues with that, mainly because
our prototypes, everything have the exact same FOD mitigation that off-the-shelf laser line triangulation has, right? So the packaging and the lens protection does not change, and that's proven technology. So no, we will not have impacts from any external material.
Okay, great. Let's see, somebody asked, can it provide operator alarm for non-conformances? Maybe does it alert the operator of non-conformances? I'm not sure exactly.
So what happens, I'll just use in placement of the example I used earlier, but at the beginning of a course, if you begin to lay the course and within 1.5 seconds, all of the things that Gil told you or showed you all happens within 1.5 seconds. So 1.5 seconds, let's say 2,000 inches a minute, 0.3, 0.4 G acceleration, you're about 4.5 inches into the course. It identifies that that lane 16 is too short, too long, it's out of compliance. The machine stops, sends a message to the control. The operator has an option to abort the course, go up there simply and pull off the 4 inches of material, 4.5 inches of material, or to continue the course. That same thing happens. We can set it so on a gap, you may not want to, on every gap, to have the machine stop, but you may want it to be reported. There's flexibility in that and how the HMI or the HMI sends or displays the messages. But yes, it does report, and it can create an action, which in the example I gave, it stops the machine. And what that does is keep you from laying something that you know is bad.
Okay, excellent. Thank you. So next question asks, can you speak a little bit about OCT's data resolution compared to laser profilometer readings? It says TTL. I'm not sure if they meant
That's probably
line laser.
LLT.
Yeah, LLT.
Yeah,
I don't
so
know
I'll
if
pass
you
it to Gil.
data resolution in comparison.
This for us.
Yeah, so to do a good job, you have to kind of know the different constraints, right? So every system, LLT, OCT camera, has what's called a field of view, right? So that's the number of points, or in a camera sense, the number of pixels. And so the horizontal field of view, because that's where we're measuring our profile, right? The sensor's on the back. You have to put yourself on the back of a roller, just like you see in this photo. And so that horizontal resolution is really what you're most interested in. And so the width is important. So our system today is designed for a width of 4 inches. And then the number of points within that 4 inches is really your density, or how accurately you can measure things across. And it's all tunable, but we have modes where we can go up to 2,000 points per profile over those 4 inches. So you can just do the math, divide 2,000 by 4 inches.
Mm-hmm. Excellent. Can the system detect FOD or foreign object debris on the backside of the toe?
No. So you're saying if the toe is on, it's on the adhesion side of it. So yeah, we would be able to pick up if it changed the surface, the height of the surface, yes. But if it doesn't change the height of the surface, then it was flat, then it would be difficult to detect. But anything that changes the height of the surface would be identified, even if it's on the back side of the toe.
Yeah, and like a splice is a good example, right? Where we know a splice is 2 layers of toe that are stacked up on each other. And we typically like to have at least the thickness of 1 toe to be able to identify. But what you end up having to do is just, every FOD condition is somewhat unique, right? And what we can do is set up all the different examples and just run tests. And there's a large collection of FOD that we'll see. But we all know that, to see submicron FOD is difficult for any sensor.
Yeah, so most of the most common things that you see, backing film, resin balls, we'll call it a fuzz balls, or the fibers, twist, puckers, those types of things. All of the most common we can detect. So like Gil said, there might be some small anomalies that we would have to check to verify and check.
Okay, great. So someone asked, is this a development technology, or is this available to purchase currently?
Yeah, great question. So we are finished with the development. As you can see, it's on machine. It's on a running machine today. There are still some of what do we do when we identify that particular non-compliance that we are still working, which is the HMI portion of it, the front end of it. I would call the less risky part of it. Yes, we are offering it for sale now. We have been actively working this even through the COVID situation on the front end piece of it. But yeah, it is for sale. We have quoted it to several people And we have one partner that's we're very close to signing to put this piece of equipment onto another machine or machine out in the industry.
Excellent. Let's see. What sort of dimensional tolerance can it measure?
Gil, I'll let you have that one.
Yeah, so I alluded in the slide, there's different features that have different tolerances. So for gaps and overlaps, right, that's typically measured in a width. And so right now, our resolution's probably down to 5/1000ths of an inch. But we like to be conservative and say about 10/1000ths of an inch. We have to look at it at all the different angles. And so you have to really look at the worst case presentation to the sensor. You can't just use the best case presentation. And then the defects from a topical standpoint, it's really the height, which is about 1 toe dimension, which is 5/1000ths. Thickness dimension.
Yeah, excellent. So we're getting to the top of the hour here. We'll see one or two more questions here. Can you speak to how the system works for complicated shapes? You've sort of addressed that.
Yeah, I think Gil mentioned that before. One of the key features or attributes of this system is that that's what it excels at, is it can be up to 60 degrees off angle. So on a very complicated surface, it's able to collect that data. It doesn't matter if it's at normal to the surface or 60 degrees off surface. Again, we're collecting 98% of the points. And that's one of the biggest limitations of the LLT systems, which we employ. We use those today on simpler machines, ATL machines, on mild contour, because once you get above, I'll call it 10, 15 degrees, most of the data, there's not enough data there you get a lot of false positives. So that's, but yeah, complicated parts, that's one of the reasons we went with this sensor.
Yeah, so the contour basically causes the sensing surface to be closer or farther away from the part, right? So we call it depth of focus. And line laser triangulation and regular cameras have a fixed, depth of focus, which, is defined by the optics. Our depth of focus is 2 to 3 times what line laser triangulation is. So we have 25 to 30 millimeters of wiggle room, right, where the surface can get closer to us or farther away and we don't lose sight of it, and we can still take great measurements along with being able to be off axis.
Yeah.
Okay, excellent. So we're right at the top of the hour here. So we've run out of time. We're coming to the end of the webinar. We do have a few questions here that were sent in that we didn't have time to answer. These will be saved and forwarded to Robert and Gil, to be addressed offline for anybody that sent one of those in. So yeah, Robert and Gil, thank you again for this presentation. We appreciate it. Okay,
so again, I want to thank Abby, both you and Hannah, and CompositeWorld for allowing us to do this, and then too for everyone that joined today. Click the link and sign up for, we'll get a one-on-one consultation, and we can talk through how we can apply this either to your piece of equipment, or how we can, you can benefit from this technology. So really appreciate it.
Great, yeah.
Thanks everybody.
Yeah, just to reiterate, thank you everybody for joining us today. Appreciate you being here. I hope to see you again for the next CompositeWorld webinar. So have a good day, everybody.